Okay, so before I get started with the lecture material, I just want to mention a few things. So this is the second last week of classes. Um, so either when if you're in SCI210 or SCI410, you have a final exam for this unit. Just so you know, in order to pass SCI210 or SCI410, you need to get at least 50% on the final exam as well as 50% overall. This is the first time there's an exam for SCI210, so there's no previous exams, but what I'm going to do is I'll make a mock exam paper, so that has similar style questions as the final exam, and I'll release that early next week, so you guys can have a sort of a better idea of what the exam will be about. And what I'll do in the lecture next week, the first thing I'll do in the lecture next week is I will go over the mock exam by hand, sort of give you a better idea of what the mock exam, what the actual exam will be like. And then after, that might take about, I don't know, half an hour to an hour. Then after that, I'll start going through the final slide deck. I may not get through all the final slide deck, but it's available for you to go through further if you want to. So the slide deck for next week is not accessible in any way. It's not on an assignment. It's not on the final exam. It's just for your further interest. So again, I'll be releasing a mock exam early next week. Start of next week's lecture, I will go through that in class, so you guys have a better idea of what the final exam is going to be like, because this is the first time there's an exam for SCI210, 410, so there's no previous exam papers as of yet. Okay, so with that said, today we're going to look at some more advanced plotting or visualization features in MATLAB. Okay, so one of the advantages of MATLAB over other environments is the ease at which you can plot things and visualize things, right? That's one of the advantages of MATLAB. So we've looked at some basic plotting, right? We've looked at plotting basic graphs, plotting multiple graphs on the same figure using subplot. But today I want to go into a little bit more depth on sort of some more advanced features you can get. We'll look at some more advanced features of the plotting functions you've already seen. We'll look at some 3D plotting and some animation. And then finally, we'll sort of look deeper into sort of the programmatic aspects of how to manipulate plots programmatically in MATLAB. Okay, so let's look at some plotting techniques we've already learnt. Okay, so we can do these things where you have subplots, but one of the plot might be over, take up two, subplots you might say. And the way we would do this is that this first subplot, you imagine it being a 2x2 grid, and this is the first one in the 2x2 grid. For this one, you imagine it being a 2x2 grid again, and this being the second one. But for this last one, you just imagine it being two rows with one column, and that actually should be a 2 there. This is the second guy in that, okay? So these dimensions, rows, columns, don't have to be the same for every subplot. So by manipulating this, we can get a subplot sort of being the width of these two upper subplots. So we saw that when we're looking at the Roman data. When we're looking at the strontium isotopes and things like that. Okay, so actually I haven't done this yet. I did it a different way. But you have scatter, right? So this is doing a scatter plot. So in some sense, it's sort of equivalent to doing a normal plot, but say using circles as the plot. But this gives you a little bit more control over how the exact points are plotted. So this 25 here is the point size. So the larger this is, the larger these circles are. So this is for plotting these gray points here. Of course, you'd use a different color to plot the red points. We're telling it's filled in, so it's not a hollow point, and this is the color to fill it in with. Okay, so this comes back to the way you can represent colors, arbitrary colors on a computer using red, green, blue component. So this is 80% red, 80% green, and 80% blue, which gives you a light color of gray. If this was 1, 1, 1, then it would be white. If it was 0, 0, 0, it would be black. Okay. Of course, you can manipulate these things. If it was 1, 0, 0, then it would be just red. You can just Google RGB colors and you can come up with all sorts of tutorials on this. Okay. And then we also want it to have an edge, right? And we want the edge to be a slightly darker shade of gray. Okay? So it just SCAD just gives you a little bit more control over the points. Of course, you could just plot individual points using plot, but SCAD gives you a little bit more control over how it looks. Okay, so we've seen plot before. We've used bar to do bar graphs. We've used hist to do histograms. CLF clears the current figure. Figure creates a new figure window. We've seen X label, Y label, title in terms of labeling the axes and the title of the graph. We've seen subplot in terms of putting multiple axes on the same figure. And sprintf, I'm briefly mentioned sprintf and sort of, so remember sprintf is like fprintf. Remember fprintf, we give it a format string, right, and some variables to substitute into it, and it prints to the screen, or we can first give it a file ID as we saw last week, and it'll print that to a file. sprintf doesn't do any printing to a screen or file, but instead returns the string, right? So you could put, so for example, I could have, say, just a variable called 6.5, and I could say, let's go fprintf, okay? So the value of x is x, so x gets substituted into this placeholder variable, right? Okay? But let's just say I didn't want this to be printed to the screen. I just wanted to put it in a string and manipulate it. I don't want that new line there. So let's call this my string and change it to sprintf. Okay? So instead of printing to the screen, it stored that string with the interpolated value, this value inserted into this string. So this can be quite useful for constructing complicated strings for your X label and Y label and title. So although it's not particularly a plotting function, it can be very useful in terms of these other things. Okay, so as I said before, one of the powers of MATLAB is its plotting power, right? Its power to visualize things. And you can Google MATLAB advanced plots and you get all sorts of different things. You can pretty much anything you can imagine you can do somehow with MATLAB. Okay? Okay. So let's look at some new plotting functions, right? So log, okay? That's doing log plots, right? Where the X and Y labels are log scales. Semi-log X, where just the X-axis is log scale, or semi-log Y, where just the Y-axis is log scale. Area, so area is, okay, it fills in under the curve, like an area type chart, right? So you've got a curve, it fills in the area underneath. You can do complicated things like filling an area between curves, okay? Stem, okay, so these are sort of like these stem leaf plots you can do. We've already seen bar, but the way we've seen bar is sort of the bars are next to each other, whereas we can actually stack bars on top of each other or horizontally. We actually see some examples of this later in these slides. Mesh, which is for plotting like the mesh of a 3D object, so like a wireframe of like a sphere or a cylinder or some other complicated thing. Surface. So surface is like plot, but it's for functions of two variables, right? So plot is sort of like you give it an x and a y value and it plots that line. For surface, you give it x, y, z values and it'll plot a surface. So you've got a function, say, f of two variables x and y. And the z values are the values of that function at x and y. And it'll plot a surface plot of that function. Movie will let you do animation, okay? Very easy to do animations in MATLAB. We'll see an example of that later. Get, set are low-level functions we'll explore later in terms of programmatically manipulating certain aspects of figures, and you can pretty much do this for any sort of object within MATLAB. It's a very general way of manipulating MATLAB, but we'll just see it in the context of plots. Line and text, these are sort of lower level primitives in MATLAB. So if you do plot, you'll be calling these functions a lot to do the individual lines, and you can have more control over it if you do these things yourself, right? Like you may not need to do it yourself. So this, I guess, by analogy, this is sort of like plot, sort of like the load and save functions in MATLAB. It's very easy just to load data in, whereas these are the lower level file input output that we talked about last week, like things like get line, fopen, fclose, these things. So these are sort of like the lower level primitives as far as plotting goes. So they give you more control over how things look, and we'll see some examples of this. But if you don't need that, then these original plotting functions will do just fine. Okay, so the plot function uses linear scales for both the x and y axis. As I said, log scales for both x and y, semi-log x, log scale for x-axis, linear scale for y-axis, semi-log y, linear scale for x, log scale for y. Okay. So remember, in a few lectures ago, we looked at we looked at a basic population growth model of these phytoplankton blooms. And so you see these things in satellite images. So this is off the coast of New Zealand. And they can be spread around thousands of square kilometers of sea surface, right? So this is a very large area. So why are phytoplankton important? Well, they form the base of the ocean food web, right? And as they grow, they also absorb substantial amounts of carbon dioxide from the atmosphere, and when they die, that carbon sinks to the ocean floor. So they're a carbon sink. And why are they this blue color? Well, that's their calcium carbonate scale reflecting the sunlight. Okay, so we had a look at this sort of this curve that explains their population, right? So you have some sort of lag or induction phase, and this exponential phase takes over, declining growth. So say they're sort of hitting some sort of maximum carrying capacity of their environment, it levels off, and then eventually they die. Okay, so this doesn't look exponential, this looks linear, but that's because of the log scale on the y-axis, right? Okay, so let's explore this a little bit. So let's create a vector called hours between 0 and 12. Okay, so let's go time. Let's go linspace 0 to 12, and let's say on 100 points, right? So 0 to 12, 100 points. And then I want to have the cell count, according to our theory, is 100 times 0.6 times time. So that time equals 0 is just 100, but of course this is an exponential function. Okay, so I can do this 100 times exponential 0.3 times time. Okay. And we want to plot the data using semi-log y. So, okay, let's just do normal plot first. Okay, so we have time, cell count, theory, black, solid. Okay, so this is going to look like this, and it looks like our exponential curve, right? But if we put a log scale on this, it should look like a straight line. So let's do that. So this would be semi-log y, because you still want the linear scale on the x-axis. X value, black, solid. Okay, you get your straight line. This is the log scale. And of course, you put your axis labels, etc. on it. Okay. Okay. We could also simulate experimental data. Of course, it doesn't quite exactly follow this theoretical curve. Okay, so we can say add minus 50 to plus 50 to the actual theory, and let's just do that. Cell count equals cell count theory plus random I. We want random values between integers between 50, minus 50 and 50. And then how many do we want? We want one row, and we want just the length of how many is in cell count theory already, right? If you want these to be the same size, you can just add them together. Okay. And then we can, this is going to be a very jagged line, so okay. So of course, because of the log scale, it looks much because the actual theory grows exponentially, but this random component stays constant. So as we go further along in time, the random component has less effect. That's why it looks like this on the log scale, right? Okay. That's just a simple demonstration of using semi-log y. Okay, you can do semi-log x as well, right? To actually, this should be semi-log y as well, I think. Yeah, it's not semi-log, it's semi-log y because it's log scale on the y-axis, but the x-axis is still in. So that's a typo, should be semi-log y. Okay. So we've seen plot before, right? We have the simple form. We have x values, y values, plot it, title, x label, y label, right? We've seen that many times. We've seen using bar graphs quite a few times as well. Okay, we haven't seen area yet, so let's have a look at this. So year 2013 through 2017. And then the population is equal to 0.9, 1.4, 1.7, 1.3, and the last one is 1.8. Okay, so I can go area, year, pop. Okay, and that'll give me this area graph. Okay. Okay. And I can do a stem graph as well. So if I change this to stem, add these data points connected by a stem to the x-axis. Okay. So we're going to come back to this TB data we looked at a few weeks ago. This was related to tuberculosis incidences in the US among foreign-born people. Okay, so this is from a few weeks ago, but I've copied across the mat file here. So we're going to create a script called doesn't tell me what I should call my script, but I'm going to call it TB plots. Okay, I'm going to open up, I'm going to load my TB data in this mat file. Of course, this file is available on Moodle. Okay, so let's just remind ourselves of the content of the file. So let's just run this. Look at the workspace. Okay, so let's just clear everything that we've been doing. Okay, run this again. Look at our workspace. So we have TB cases, TB years. TB years are just the years. And TB cases are the corresponding number of tuberculosis cases. Okay. Create a 3x2 figure that plots the year and cases data using plot, scatter, bar, bar H, area, and stem. So 3 rows, 2 columns. Okay. So we clear any current figure. Then we do our first subplot. So 3 rows, 2 columns, first subplot. This is just plot. TB cases, TB years. Okay, X label is year. Y label is TB cases. I just want to copy and paste this. Okay, 2. So what is it? Scatter bar. So after bar, I've got bar H, area, then stem. Okay, so what's my error? Oh, I've made it the wrong way around. TB years, TB cases. Okay, so we get our plot. We see this is using plot. This is using scatter. This is using histogram. This is, sorry, a bar chart. This is using H bar, so it's horizontal bar chart. So I actually should swap the X and Y labels, shouldn't I, for that one? So for H bar, I should, because it's going to be horizontal bars. So that's going to be the Y label, the X label. Okay. Okay, year TB case is going to be the area graph, and it's going to be the stem graph. Okay. So which figures best represent the data? Okay. So let's have a look at this. Okay. So which thing do you think best represents the data just by the default values? Well, personally, I don't think this one does well because we actually only have discrete data points at each year, and then we're connecting them, which gives the erroneous perception perhaps that we actually have measurements between those years. So I don't think that one's good. I don't like the default scatter because it can look a little bit misleading. This value looks like a lot higher than this value, but then I realized that the scale is not going from 0. Okay, I think this one looks pretty good. Okay, you see the full Y scale is not, so we just have one data point for each year, just not connected by lines. Okay, I mean, the same could be said here, but I think it looks a little bit crowded, so I think this aesthetically looks better. Again, here it's the same as this. It can give the erroneous perception that we have measurements between the actual years. And this one looks fine as well, I think. So I think it's either this one or this one because both of the positive aspects are shared. It's just a single data point for each data point we have. And we see this whole Y scale. So either one of these, I think, would be the best. Okay. Okay. Of course, you could change the Y-axis for this one to make it the full Y-axis. And in that case, that one looks all right as well, right? It really depends. Okay, so this one, okay, so maybe you choose this one, but I think these two. But I think this one, the stem plot's also all right. Okay, so what do we see here? When I was doing this, I copied and pasted a lot, right? So when you're programming, if you copy and pasting a lot, there's probably a better way of doing it. Okay, so if you're copying and pasting a lot, it's a good indication of there's a better way of doing it in programming. That repetitive thing should be done by the computer. And when you're copying and pasting, it's very easy to copy errors and not change things. So it's an easy way to introduce bugs into your program. Okay, so to motivate that, we're going to look at the eval function. The eval function is used to evaluate a string. Okay, so let's just say I have so this is a string, right? It's just text. It does nothing in MATLAB. It's just text, okay? But represents some MATLAB code, right? That's valid MATLAB code in there, right? Let's just say I have this string and I want to MATLAB to run it as if it was MATLAB code. I go eval that string. Or evaluate, okay? So eval is a way of running code that's within a string, okay? Okay. So I see here, the only thing that changes for each of these is the function we're calling, right? Except for bar h, which is a little bit different because the x label and the y label has changed. So let's just treat bar h as something unique. And let's just make bar h the last in my subplots. So bar h, I'm just going to leave by itself, right? But all these other ones look very, very similar, right? Okay. So I'm doing the same thing over and over again. So maybe a loop, for loop. Okay, for I is equal to 1, I go from 1, I do 5 plots, 5. Okay. And, okay, so this should be I, right? This is the ith subplot. Then the x label and the y label stay the same for each, and what changes is plot, scatter, etc. Okay, so let's create a cell array for these function names, the strings. Okay, so let's call it function names. There's going to be a cell array of strings. So the first one is called plot. The second one is called scatter. Then bar, then area, and the last one is stem. Okay. So we have everything we want. So let's get rid of all this repetition. Let's indent it so it's well styled. Okay. So what I want to do is I want to build a string here that has the corresponding function name at the beginning and this at the end. Okay. One way I can build strings is using sprintf, right? Okay. Let's try that. Sprintf. What do I want at the beginning? I want the function name. So this is going to be a placeholder for a string, which I'm going to insert in. Then actually TB years, TB cases. So the only thing that changes is this first function name, right? Okay. And then I want to splice in this function, the corresponding function names, right? I'm after the ith one, right? And remember, when I'm getting stuff out of the cell array, I have to use curly brackets. Okay. So that will build the string that I want, and then I want to call that as MATLAB code. So I put eval around it. Okay, so I've gotten rid of a lot of repetition, right? And I mean, this is what you use a computer for, right? Is to get rid of repetition. Okay, that's exactly the same thing. Okay, so eval is pretty powerful. But also be careful, okay? So for most of the stuff you're doing, it's going to be fine. But so let's just say you're accepting user input from the user, and you're putting that user input into eval. So the user can type in arbitrary code and then evaluate on your computer. And then if the person entering it doesn't like you, they could enter all sorts of things that stuff up your computer, right? So when you're putting stuff into eval, that's accepted from a user, that's not just built by you, then you've got to be very, very careful, okay? But for most of the things you'll be doing in a scientific context, you don't have to worry about this. But in terms of general computer programming, this becomes an issue, say, when you're doing web programming. Users are entering things, and then if you're not careful, they can delete entire tables from databases, etc. Okay, so just a word of caution there, but you probably don't have to really worry about that. Okay. Okay, so another case would be, let's just say we want to load a sequence of files, right? Well, we can just go load and copy and paste this and change the number. But what if there was 1,000 files? That would get onerous and pointless. Just loop over them, build the MATLAB code as a string. So I'm just inserting this I in here. So load file 1.dat, then load file 2.dat, and then eval it, right? Okay. Okay, so this is essentially what I just did before. Okay, I just put these in a cell array. It does it in a slightly different way. Just have a think about how it does it. It just pulls the function name and does the concatenation operator to join this onto the end. Okay, so the as printf is fine. This is also fine. Just two different ways of doing the same thing. Okay, so this is what I just went through before. Okay, so that's eval, right? Very powerful. Okay, so let's have a look at bar a little bit more closely. So we have these three sets of data. We have x1, which is 2, 4, 7, 10. And we have x2, which is 4, 6, 12, 8. 4, 6, 12, 8. Okay. Yeah. We have x3, 1, 2, 1, 4. Okay, let's put that all into a matrix. So x1 is the first row, x2 is the second row, and x3 is the third row. Okay. Okay, then let's create a bar of all that. Okay, so what it does is this first section is the first row, and for each of these individual things, just the individual 2, 4, 7, 10. Okay, and then the second row is this second group, 4, 6, 12, 8. 1, 2, 1, 4. Okay, so that's how it does it. Okay, you can change the color. The default colors are used. So if I go color map bone, and then redo the plot. I think I have to redo the plot after I change the color map. No. What am I doing wrong here? Okay, so I think that's how I have to do it. So I do the bar chart. Okay, then I do color map bone like that. No. Let's try bar. Okay, no. Oh, why is this happening? Okay, documentation. Let's try it this way. Let's put the, so I'm storing the axes. Okay. Then I go color map axis bone. Color map. Okay, I'm not exactly sure why this isn't working, but let's skip it for now and come back to it later. Okay, so what should happen is you can change the color map and that will change the default colors that are used on those plots. Okay, these are different color maps that are built into MATLAB. You can create your own, but these ones are in there by default. Okay. We can also, instead of plotting these side by side, you can stack them on top of each other by using stacked. Okay? Okay. Let's try it again. I don't know why it doesn't want to work for me. Okay, so we can stack them on top of each other. Okay. So let's do this. So let's look at TB data ethnicity. Let's create a new, so this TB plots, okay. So let's just put a comment, original TB data, TB data broken down by ethnicity. I want to create a new figure window for this. Okay, I don't want to put it on the same plot. Okay. And then here I want to load the data as well. So this is TB data ethnicity.mat. Okay. Let's just remember what's in that file. So let's clear all. And we just load TB data ethnicity.mat. Let's have a look at what's inside there. And we've got TB years like before, but instead of just having TB cases, we have this broken down by the origin of the foreign-born person, right? So from Africa, from Asia or a Pacific island, Hispanic, and white, so I guess of European descent. Okay. Create a stacked bar plot of the data. Okay, so let's do that. Okay, so how do we put all the data together? So remember, each data point is a row, okay? And so we have, say, TB African. Oh, yeah, that's what I meant. TB Asian Pacific. Okay, so I want these first values to actually form the first row, right? The second values of all these to form the second row, etc. Okay, so how do I do that? So I could go TB African, okay, like that, and then put, say, TB Asian Pacific like that. You just put the further ones across like that. So let's do that. So let's call it all data. Okay, then we have TB Hispanic, TB white. Okay, and we can go bar all data and stacked. Okay, create a stacked bar chart. Maybe you want X and Y labels. So X label is year, Y label is TB cases, case count maybe. Okay. So another thing we want is you actually want the actual year numbers here, right? And actually, a strange thing is going to be happening because actually our years, if you look at TB years, it's actually in reverse. So the data currently, this is the 2013 data, this is the 1993 data. So it actually looks like it's increasing, right? Which is the opposite effect we'd Okay, so we want to fix this up. So the first thing we might want to do is put a different X label on it. So let's just look at, if I go bar, okay. Okay, so I can give it XY values if I want to. Okay, so let's just do that. Okay, so this is TB years. Okay, so if I ran this, okay, so it sorts out the years properly now, and we get this decreasing effect like we would expect, right? Because now it associates the first row on that to the first element of this 2013, and it's going to plot the axis in increasing order. Okay, everything's fine again. Okay, so maybe we want to put a legend on this to describe what the different colors represent. Okay, so let's do that. Let's go legend. Let's go African, Asian or Pacific Islander, Hispanic, European. Okay, so I have my thing, and of course you could change this if you don't like it there. You can drag this down to here. You can do whatever you want. Maybe drag it across to there. Okay, so you have this basic plot. Okay. Okay, so what I'm going to do is I'm going to pause here, come back at about 3 and continue. So just before the break, we had a look at these TB cases broken down by ethnicity, and we put it in a stacked bar plot. Okay, something like this. Okay. Okay, so we can customize plots. So for example, let's do these plots again. Okay, so I can go say tools, and so many options. So I can do insert. I can go insert a color bar. So that gives me, this is off the color map, which I mean, it doesn't really mean anything for this particular data, but let's just say you're doing a surface plot where the height of it was associated to this color map, then this could be useful. You can also just insert X labels and Y labels like this instead of doing it in your code, but of course doing it in your code it's easier, particularly if you're generating lots of plots. You can, of course, put text boxes in here and go say hello. So you can do all sorts of things with these things just by editing this window, okay? But if you're generating lots of plots, it's going to be easy to do it with your MATLAB code, and anything you can do like this in here, you can do with your MATLAB code. Okay, so we'll get to doing this stuff with MATLAB code in the last part of this lecture slides. I just want to go on and talk a little bit about animation first. So Comet is a thing to sort of animate a standard plot. And movie is something you can use to record frames one by one and put them all into a movie. So we'll see some examples. Okay, so let's just say I've got X values from -2 pi. Okay, let's just say I create some values like linspace minus, I'm going from -2 pi through to +2 pi. Let's just say I want 1,000 values. Okay. What I'm doing is I'm plotting the sine function. Okay, if I just do normal plot x, y, okay, I get what I expect. If instead I go Comet x, y, Okay. You might think that's cool. Okay. You can also do a movie. Okay. So let's create a new script. Let's call it new file script movie exam. Okay. So let's say we so what we're going to do is we're going to have the same x values minus 2 times pi through to 2 times pi, so 1,000 points. There we go, y is equal to sine of x. Okay. Well, we're just going to plot one of these points at a time. Okay. And then we're going to combine it all into a movie. So I'm going to store each frame of my movie in this array m. I'm just going to set equal to empty first. Okay. And then I'm going to go through all my elements, so through how many I have, so length of x. Okay. So here I'm going to go plot. So I'm going to do my plot. I'm going to go plot just the ith value and the yth value. Okay, using say a blue circle. Okay, so I'm just plotting one point. So essentially, you will have this blue circle moving across the shape of the sine function. Okay, I also want to set up my axes. Okay, so I want my x-axis to go to from minus 2 pi through to 2 pi, and my y-axis say from minus 1.1 through to 1.1, so I know that the range of the sine functions from minus 1 to 1. So I'm just going to create a little bit of extra space. Okay. Okay. Then I'm going to call get frame. Okay. This saves that plot frame and puts it in this index. Okay. So at the end of this loop, I've generated all these frames. Okay. And then what I can do is I can call movie end to play that movie. Okay, so if I just run this, it's going to go through and do all of this hopefully, but I think I've made an error. What have I done? Okay, so this represents a double. I just want to clear it so I know that nothing's there. Okay, so how am I going to do that? I'm just going to go clear M, just to make sure that nothing's in M, right? Before I start using it to save these frames. Okay, so this is just doing the plot by plot. So it's just generating all these different frames, 1,000 frames. Okay, so all these frames are now saved in this M. Okay, so now I can call movie M, and that will play all those frames for me as a movie. Okay, if it's going a little bit too slow for me, I can speed it up. So let's go movie. So what does this tell me? To add this number of times you want to play it, you can give it frames per second. Okay, that tells me how many frames it wants to do per second. Okay, so let's try that. So I want to play it once, and I want the whole movie to last, I don't know, 5 seconds, say, right? So how many frames per second? I've got 1000 frames I need to go through in 5 seconds, right? So I can simplify that down, but I'm not going to bother. Okay, so the whole thing will last 5 seconds. Okay, if I want it to go really fast, let's say everything 1 second, so that's 1000 frames per second. Okay, so it doesn't look much faster. There's sort of a limit to how fast MATLAB can redraw and display, but if you were to save this to a MP4 file, then it would look much faster. Okay, let's say it goes over 10 seconds. You get the picture. Okay, so you just draw, save the frame, and you can call a movie on it to generate a movie of it. Okay. So that's some basic animation, okay? So let's look at 3D plotting. So many of the 2D functions have 3D equivalents, okay? We have plot3, we have bar3 horizontal, dem3, and comet3. We use Z label to label the Z axis in our 3D equivalents. Okay. So what do I want to do now? I want to do this. Okay, so this is the formula we're going to use for the wind chill. Okay, so we have various ambient temperatures in degrees Celsius, and then we have the various velocities of the wind speed in kilometers per hour. Okay, so what we're going to do, first, I'm going to create a new script. Called wind chill bar 3D. Okay. And then inside the script, I'm going to create an internal function, a sub function, so to speak, that was going to give me the wind chill temperature, given the ambient temperature and the speed. So I'm going to call it temp, speed, and okay, and then this is going to be chill temp. So chill temp. Okay. So this I use v to the power of 0.16, so I'm just going to store that in a variable called x, say. X is equal to speed to the power of 0.16. Okay, so what do I do? I got 13.112. (6215T). 1137X. Zero 0.3965. 3965 times temp times x. Okay, I believe that's right. Okay, so I have this function for my wind chill. Okay, let's just put this in a different file. So it's a new file, new function. Let's call this wind chill m. Remember, the function name has to match the file name. Okay. So what am I going to do? So I'm going to have a range of temperatures, ambient temperatures, I'm going to go over, and a range of speeds. Okay, so temp, let's say I want to go, say from -20 to say 30 in steps of 10 degrees Celsius. Okay, and let's say the speed I want to go is from 0 kilometers an hour, so no wind speed at all, to 10 kilometers an hour, say in steps of 2. So 0, 2, 4, 8, 6. Okay. So what I want to do is I want to create a grid of values. So I've got, so if I just ran this, but if you imagine this is actually a two-dimensional function, right? So it's plotted over the two-dimensional plane. So what I want to do is say, let's say the temperature is my x-axis and my speed's my y-axis. I'm going to use this function called mesh grid, and it's a little bit easier to explain what it does if I just do it and explain the output. Okay, let's go x, y, mesh grid, temp, speed. Okay, so what's going to happen is this is representing the two-dimensional sort of axes that my function is going to be plotted on, with the x-axis being temperature, the y-axis being speed. This is like my x-axis. So this is the temperature value on this grid. Remember, temperature is just the x-axis. So if I move into y-axis, it doesn't change. But if I move in the x-axis, I get my different temperature values. Okay, and y is going to be my speed. And so if I move in my y-axis, it's going to increase, but if I move my x-axis, it's not going to increase. And then over this grid, I want to calculate my z values, okay? I could do it in a loop, but I can just vectorize it all, okay? So I could go z is equal to wind chill, just put it all in as these matrices. But then I have to come back here and make sure that this is all going to work over vectorized values, not just scalar. So I have to remember my dots, okay? This is just timesing by scalar, so that's fine. Timesing by scalar, this is fine. To have a dot, okay? Okay. And then I can do a bar 3, I think it was. So let's just x, y, z. X label is ambient temperature. Y label is wind speed. Let's say kilometers per hour. Degrees C. And Z label is perceived temperature. Degrees C. Let's put a title. Wind chill. Let's plot this. X must be a vector. What am I doing? Okay, so I'm only going to be doing Z. Okay, so this, of course, we want to change these scales eventually on these axes because this doesn't represent exactly what's happening. This is 0, 2, 4, 6, 8, 10. This is -20, -10, 0, etc. But we see that what we expect to see, right? We see that as the ambient temperature increases, then the perceived temperature should increase, right? That makes sense. But then we see as the wind speed increases, wind speed increases down this way, sorry, then the perceived temperature decreases, okay? And so let's just say for the wind speed here, which would correspond to 10 kilometers an hour, and here, which would correspond to minus 20 degrees Celsius ambient temperature, we see that we get, say, a minus 30 degrees Celsius perceived temperature. Okay, so we have this plot. Three-dimensional plot. Let's go bar 3. So there's going to be some options we can set to change the numbers on the x and y axes, but this was just demonstration, so I'm not going to really bother about that here. So I'm going to move on to some other 3D things you can do. Okay, so let's look at a spiral. Okay, so let's say I've got t values. So let's just say these are my z values. So I'm going to go from 0 through to 10, say, in 1,000 points. And then the x value is going to be cos of z. The y value is going to be sine of z. Then I can go plot 3, x, y, z. It's going to give me this helix shape. Okay. I can go for long if I come up here again and go z. Let's go through to 100, say. Maybe that's too far. Let's go through to 40. And come up here and recalculate the x, and recalculate the y. And come up here and do the plot again. Okay, so I get this helix. I also have Comet 3, which sort of does the same thing as Comet, but for this three-dimensional. Okay, so it will animate this helix. Like so. Okay. Okay, so we have these mesh functions, which draws a wireframe mesh of 3D points. So we can use cylinder to generate the mesh, and then we call mesh. So for example, let's say I want a radius of 2. I'll explain exactly what these things do in a second. My list of x, y, and z points to plot. Cylinder are steps. And then I go mesh x, y, z. Okay. Give me a mesh, a cylindrical mesh. I can change the face color to a gray I want, or I can come up here and go face color. Let's say I want it to be a light red, so that could be something like 1, 0.5, 0.5. A pinky color. Okay. If I decrease this to 10 and did the mesh again, sorry, I didn't need to generate the cylinder again. Then do the mesh again. It's got less. So that's pretty much, that circ steps is pretty much, so it approximates the circle by a regular polygon, right? And circ step is pretty much the number of sides of that regular polygon. So the higher it is, the more circular it's going to look. Okay. We can call cylinder, but tell it that we want to start with a radius of 0 and go to a radius of 2. Okay, so it's not going to be a cylinder per se, but it's going to be a cone. So for example, we can go cylinder. Let's go from 0 through to 2. In terms of the width of the cylinder, it's going to generate me a cone. When I plot it, it's going to be cone. Okay, and I can actually give it a series, like a function, like a series of 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 radius values. So give me something like this. Okay, so for example, I go from 0 through to 4 pi. Let's go in steps of 1,000. Sorry, 1,000 number of points. The radiuses that I want to use is sine t. So the first value in here will be the first. So the width is going to look like the sine function. Going to come undulate in and out. Then I'm going to create my cylinder using these r values. Okay. Then I'm going to use this in my mesh. And of course, if I say increase circ steps, say to 100, so it's going to look a little bit better. And I'm not going to do this phase color anymore. I'm just going to go X, Y, Z. Oh, I'm going to generate my mesh again, sorry. Okay. And then I'm going to plot it, but without the face color. Okay, I get something like that looks like that. And then I can, okay, if I just do it again, I can call color bar, and I'll put a color bar on it for me, okay? So this is the Z value, 0 through to 1 gives me the color, okay? Okay. So surf creates a surface plot, so similar to here, I can get the X, Y, Z values of a sphere. So I can go X, Y, Z sphere. Let's go 10 say. Then I can call surf X, Y, Z. Okay, plots a sphere. This value, so again, it approximates a sphere by these regular polygonal shapes connected together. And then if I increase this value here, it's going to do it more accurately for me. Okay? Okay, so if I generate this, I can go File, Save As, and this will save it to a file, of course. But if you're generating lots of plots that you want to save to file, you can do it programmatically as well. You can print -D, so this TIFF is the file format. So this is as a TIFF file. You can use PNG, JPEG, or your standard image formats. This is the DPI, the resolution, the dots per inch. So higher this is, the sort of the nicer it will look. And this is the output file name. Okay. If you don't put the output file name, you will print it to a connected printer. You've got to print it connected. Okay. So in MATLAB, each figure consists of different objects, and each object is assigned a handle. Okay, so objects within plots or within the figure window include lines, text, axis, etc. Includes all different types of things. Right? You've got these text for the labels, you've got axis, you've got individual lines making up a plot. And the object handle is a unique real number that is used to refer to that object. The various plot functions return a handle for the plot object, which can then be stored in a variable and used later to refer back to that particular object. The handle will remain valid as long as the object exists. So if you close the figure window and try to use that object handle, still weird things will happen. Okay, so this is organized in a hierarchy. The objects are organized hierarchically, and there are properties associated with each object. The figure window and axes are parents. The axes are used to orient its children, which include plot objects and core objects. So you've got a set of axes, then you've got lines plotted on these axes, and the lines will be sort of children of the axes object. Okay, so you've got this sort of hierarchical organization. You've got a figure, then you've got axes, then you've got plot objects, which just produces different plot types like bar charts, area plots, and you've got these core objects, which are the graphics primitives, including lines and text. So it's parents down to children. Okay, so let's have a play around with this. So let's just say, let's just clear all this, and let's just say I've got x linspace 0 through to 2 pi, let's go 100 points, y equals sine of x, plot x, y. Okay, standard plot. But let's just say I want to programmatically edit this. I want to save the handle that the plot returns. I'm going to go h is equal to that. So now h contains the graphics handle. H contains its graphics handle. Okay, it actually contains all the things here. Okay, so if I call get h, or just type h into the command window, but get h will display all the properties available for that. Okay, and then we can change any of them that we want. Okay, so for example, let's say we want a very thick line. We see that line width is currently 0.5. Okay, so I'm going to come down here, set, pass my handle, which I've stored in h. Line width is the property. It's currently 0.5. Let's say I want 2. Okay, changes it. Okay, let's say you can even change its x and y data, right? It's got x, y data. Change it if you want. Let's say I wanted to plot cos instead. Okay, so I go set h. So the x data is the same, but the y data is changing, and I want to go cos of x instead of y of x, or sine of x rather. Okay, cos of x. Okay, so h refers to this plot object. We can use get h to get all of its properties, and then we can use set to manipulate it programmatically. So this becomes very useful if you're doing lots and lots of plots. You can programmatically edit it and do all sorts of fun things with it. Okay, so for example, you put the property name as a string and just the property value as the next parameter in this in this set function. Okay. How many slides do I have left? Do you guys mind if I go for like an extra 10 minutes just to get through these slides? Because you sort of need these slides for the last assignment. Okay, so, okay. Okay, so this is just going through what I just, so you can get individual, so okay, get of h as just returns all the properties. I can pass it just a particular property I want, and it will return that single property. Okay. I've just shown you an example of using set, right, to change the properties. So you can change the line width, change the color. So I want set h, I want the color to be green now. Okay, green. Okay. And you can do all sorts of cool things. You can set 2 properties at once. Okay, you just put your handle, the property followed by the value you want, another property followed by the value you want. So you can set multiple properties in one core. Okay, you can set these properties when you originally call plot. Okay, so if you wanted these from the start, you could just set from the start, or you can change it later using set. Okay. So core objects are the basic graphics primitives that are the building blocks for the other objects. So the functions that create core objects include line, which is a single just line, text, which is a text block, rectangle, patch, and image. Okay. So we're going to focus on line and text. When these functions are called, the handles can be stored in variables so that we can use get and set to modify them. Okay. So line, so this is, we've got our x data, which is exponential decay. So time, x of minus time, uses line to create that. And it passes these extra parameters, and so what's line with 2, color k. Of course, we could use set later to change those. We can use text to put text on our plot. And we can use backslash special character to insert a range of special characters. Okay, so let's have a look. So let's go x is equal to 1, goes 1 through to what? 20. So let's go t equals 1 through to 20, y equals x of minus t. Okay, I can go create a line with these values. Let's say I want my line width to be 2. I want my color to be blue. Of course, I can change these later using set, right? I want to store this in a handle, so I'm going to go line, actually just go h line. H stands for handle. Okay, so actually I'm going to clear my current, I'm just going to create a new figure. Okay, and then I'm going to create some text pointing to this eighth data point. So I want h handle for my text. I'm going to call it text. Okay, so where do I want it pointing to? I want it pointing to the 8th data point. Okay, so get my t and y for the 8th point. So that's the position I want. I want the text to be, say, 8th data point with an arrow pointing it. And so I can go backslash right arrow. Okay, backslash thing creates a special character. Okay, so that's my 8th data point there. So maybe I'm doing something different than in the slide. So let's close this and modify it a little bit. There's my T. Create the line. Let's say I'm doing it for, say, this 3rd data point instead. Okay. Oh, and it's actually the other way, right? I want the arrow going the other way. Okay, so it's just going to draw over the top, which is not what I want. So I'm going to go CLF to clear that figure. Draw the line again. Draw the left arrow 3rd data point. Okay? Okay. I can say, well, okay, I want this to be larger font. Like it looks a little bit small to me. So remember I've got the handle in H text. So what I'm going to do is I'm going to go get that and just look at all the properties and look at which one corresponds to the font size. Okay, so I've got font size. Okay, so let's change that. So I'm going to go set, handle for the text, my font size, and let's go 20. Text is much bigger now, okay? Let's say I don't like Helvetica. Let's say I want to change my font. Where was the font? Font name. To Arial. Font changes. Okay, let's say I want Times New Roman. Font changes. Okay. So one good point is don't close the figure window because all your handles become invalid. Okay, keep the figure window open. Always label your plots. Okay. Choose your plot type carefully in order to highlight the most relevant information. That's the end of these slides. Yeah, okay, so as I said at the beginning of the lecture, I will put together a mock exam paper, release it early next week, start of next lecture next week, which is the last lecture of the trimester. I'll go through that and then just finish off the last slide deck. Okay, so I hope you guys have a good afternoon.